For decades, humanity has looked to the heavens, captivated by the rusty, dusty allure of Mars. We have sent orbiters to map its surface and rovers to crawl across its craters, but these robotic explorers can only do so much. The ultimate prize, the key to unlocking the red planet's deepest secrets, lies within its rocks and soil. Scientists believe that bringing physical samples of Mars back to Earth is the most crucial next step in planetary exploration. These returned samples could hold the definitive answer to one of the most profound questions we can ask. Are we alone in the universe? The rocks might contain microscopic fossils or chemical traces known as biosignatures that prove life once existed or perhaps still exists on another world. The excitement surrounding a Mars sample return mission is immense because it would allow for unprecedented scientific analysis. On Earth, scientists can use state-of-the-art laboratories and massive, powerful equipment that is far too large and complex to send on a spacecraft. They could study the Martian material with a level of detail and precision that rovers can only dream of. Researchers could analyze the planet's geological history, understand its climate evolution from a once wet world to the cold desert it is today, and assess potential resources and hazards for future human missions. Bringing Mars to Earth is not just about finding life, it is about writing the complete biography of our planetary neighbor. Imagine holding a piece of another planet in your hand, a rock that has sat undisturbed for billions of years, witnessing a history entirely separate from our own. This is the tangible promise of a sample return mission. Every grain of Martian dust could tell a story about ancient rivers, volcanic eruptions, or atmospheric changes. The scientific community eagerly awaits the chance to scrutinize these samples, applying diverse techniques to extract every bit of information. The potential for discovery is nearly limitless, promising to revolutionize our understanding of how planets form and evolve, and our own place within the cosmos. The quest is not just for rocks, it is a quest for knowledge and context. This mission represents a monumental leap in our exploratory capabilities, moving beyond remote observation to direct, hands-on investigation. The samples would become a global resource, studied by generations of scientists for decades to come, much like the Apollo lunar samples continued to yield new insights more than 50 years later. Each analysis could open new avenues of inquiry, sparking further questions and driving new missions. The scientific payoff would be immeasurable, providing a foundational dataset that could reshape textbooks and inspire the next generation of explorers, engineers, and scientists. The race to be the first to bring these precious materials home is therefore a race for a historic scientific treasure. For years, NASA was the undisputed frontrunner in the quest to retrieve Martian samples. The agency's ambitious Mars sample return mission began brilliantly with the successful landing of the Perseverance rover in February 2021. The rover has since been diligently working in Jezero Crater, a location believed to have once been a river delta, making it a prime spot to find signs of ancient life. Perseverance has already collected an impressive cache of over 30 geological samples, sealing them in pristine titanium tubes. In fact, NASA has described some of its findings as the clearest sign of life we've ever found on Mars, making the retrieval of these specific samples an incredibly high-stakes endeavor for the scientific community. The original plan was a complex, multi-stage ballet of advanced robotics. It involved sending a lander to Mars to pick up the tubes left by Perseverance, launching them into Martian orbit with a small rocket, and then having an orbiter capture the sample container for the long journey back to Earth. This intricate architecture was designed to be robust and reliable, ensuring the precious cargo made it home safely. However, this complexity came with a staggering price tag. The projected cost began to spiral out of control, ballooning to over $11 billion, a figure that caused alarm among policymakers and within NASA itself. By 2024, it became clear that the original Mars sample return plan was no longer feasible. NASA officially deemed its initial strategy untenable due to the escalating budget and a timeline that kept slipping further into the future. The mission became a victim of its own ambition, facing severe scrutiny from the White House and Congress. The situation grew more dire in 2025, when the White House's proposed budget for the next fiscal year suggested terminating the mission entirely, labeling it as grossly over budget. This, combined with a broader proposed 24% cut to NASA's overall science funding, has thrown the entire American sample return effort into a state of jeopardy and uncertainty. Now, NASA is scrambling to find a way forward. The agency has been tasked with developing scaled-back, more affordable alternatives, but even these revised plans face significant hurdles. Without immediate and substantial funding, any American effort to retrieve the samples is unlikely to see a return before 2035 or even 2040, if it is not canceled altogether. The meticulously collected samples from Perseverance currently sit on the Martian surface, waiting for a ride home that may never come. America's dream of being the first nation to bring back a piece of Mars is stalled, its pioneering lead now evaporating in the face of budgetary constraints and political indecision. While NASA's plans have faltered, China has been moving forward with a clear, focused, and ambitious strategy. The China National Space Administration is preparing for its Tianwen-3 mission, a direct and efficient plan to retrieve Martian samples and bring them to Earth. Scheduled to launch in late 2028, this mission aims to return at least 500 grams of material by 2031, a full decade ahead of NASA's most optimistic revised timelines. China's confidence is bolstered by a string of recent successes, including the Chang'e 5 mission that returned lunar samples in 2020, and the historic Chang'e 6 mission that brought back the first-ever samples from the moon's far side in 2024. The Tianwen-3 mission architecture is designed for speed and simplicity. It will use two powerful Long March 5 rockets. One rocket will launch a lander and an ascent vehicle, while the other will launch an orbiter and a return module. Once on Mars, the lander will get to work quickly. It will use a robotic arm to scoop up surface soil and a drill to collect deeper material from up to 2 meters underground, providing a more comprehensive geological sample. China is also considering deploying a small robotic helicopter, or a 6-legged crawling robot to gather samples from nearby areas, expanding the mission's reach beyond the immediate landing site. The primary scientific goal of Tianwen-3 is the same as NASA's, to search for signs of past or present life. To maximize the chances of success, the China National Space Administration has pre-selected 3 potential landing zones, Amazonas Planitia, Utopia Planitia, and Christ Planitia, that are known for ancient water activity. Within these zones, they have identified 86 specific sites that are thought to be prime locations for preserving biosignatures. The lander will be equipped with advanced instruments, including a subsurface penetrating radar to study geological layers, and a Raman or fluorescence analyzer to detect organic compounds on the spot, helping to guide the sample collection process. After collecting the samples, the ascent vehicle will launch them from the Martian surface into orbit. There it will rendezvous with the waiting orbiter, which will capture the sample container and begin the journey home. To prepare for the arrival of this extraordinary cargo, China is already constructing a specialized high-containment facility near the city of Hefei. This laboratory will ensure the samples are handled under strict biosafety protocols to protect both the Martian material from earthly contamination and our planet from any potential extraterrestrial hazards. With a clear timeline, proven technology, and dedicated funding, China is poised to make history. The differing fortunes of the American and Chinese Mars sample return missions have created a clear and compelling space race. At this moment, on the last day of September 2025, China is not just participating, it appears to be winning decisively. With a launch date just 3 years away and a return planned for 2031, China's Tianwen-3 is on a fast track to success. In stark contrast, NASA's Mars sample return mission is mired in delays and financial uncertainty, with no clear path forward. If China succeeds, it will be the first nation to bring back samples from Mars, achieving a monumental scientific and symbolic victory years before the United States could possibly catch up. For China, winning this race would be a Sputnik moment for the 21st century. It would unequivocally establish the country as a leading power in deep space exploration, shifting global perceptions of technological and scientific leadership. Such a success would be a source of immense national pride and would demonstrate the effectiveness of its state-led long-term approach to space science. In a move to bolster its international standing, China has even opened the Tianwen-3 mission to global partners, offering payload space on its orbiters. This contrasts with the ongoing political tensions that prevent collaboration between the United States and China, positioning Beijing as a new hub for international space cooperation. The implications of a Chinese victory extend beyond geopolitics. While the scientific community would celebrate the return of Martian samples regardless of their origin, a Chinese-led success could spur the United States into action. Alarmed by the prospect of being left behind, U.S. lawmakers are already beginning to react. In June 2025, Senator Ted Cruz introduced a bill to allocate nearly $10 billion to win the new space race with China, a sign that the competitive spirit that fueled the Apollo era may be reawakening. This renewed competition could lead to increased funding for NASA and a broader acceleration of space exploration initiatives from both nations. Looking ahead, the successful return of the first Mars samples, whether by China in 2031 or by the United States at a later date, will mark the beginning of a new era of Mars exploration. The analysis of these samples will drive the science for decades, informing our plans for future robotic missions and, eventually, human expeditions to the Red Planet. The race may have a winner, but the ultimate prize is shared knowledge for all of humanity. Regardless of who gets there first, the arrival of Martian rocks on Earth will ignite a new chapter of discovery, bringing us closer than ever to understanding our place in the solar system and answering the age-old question of whether life exists beyond our world.